Now that we've covered a bit of genetics and how to describe the genetic makeup of a population in terms of genotype and allele frequencies, let's return to genetic drift. So genetic drift, again, is the change in allele frequencies that occurs by chance without any direction that we might see coming from a force like natural selection, for example. So there's no direction. It's a random process here. But it nonetheless is an evolutionary force and can have an effect, can change the makeup of alleles in a population. So genetic drift is important from a management perspective or a conservation perspective because it tends to affect small populations much more than larger populations. So as our tiger population gets smaller and smaller, for example, it can have more susceptibility to this random process of drift. What are some of the results? Well, drift, which we'll demonstrate shortly, can lead to the loss of particular alleles in a population. And not only that, it can lead to some alleles becoming fixed in that population. So there's only one allele that every individual carries. Is that important? Well, it's certainly something to consider because it can lead to lower amounts of genetic diversity in that population. And in some cases, that might have an effect on the biological fitness of those organisms. So there may be some concern here. Okay, to demonstrate how this works, how it plays out in a small population, let's consider again another tiger population. Let's consider a population that's very small that consists of 5 individuals. So 5 tigers in this case. And let's say that there's a gene we're interested in, a particular gene located at a locus. And there are 2 forms of that gene. There's the A1 and A2 form, P and Q. And let's say that P and Q are equal, right? So the frequency of A1 is 0.5 and the frequency of A2 is 0.5. Each allele occurs in half of the population. So let's say our tigers now are allowed to randomly mate. Is that reality? Maybe in some circumstances, but let's just assume that there's random mating that occurs between those individuals and they produce 5 new offspring. What would the genotypes of those offspring look like? Well, we would expect the genotypes to be random combinations of the alleles that the parents contributed. So we would have random genotypes in those offspring. So remember, one allele is contributed by the father and one allele is contributed by the mother. So if we had a father, let's say, that had a heterozygous genotype, it was A1, A2, its gametes now would be either A1 or A2. So its sperm would either have, an individual would have A1 or it might have A2, and one of those would connect with a female gamete at fertilization. So we'd expect a random genotype in our offspring. So let's simulate this process and then go from there. So we have 5 tigers and we're producing 5 offspring. So those offspring then would have a total of how many alleles? They would have 10 alleles. So to simulate this random process, let's begin by selecting 10 numbers. We'll call those numbers 0 through 9. There are 10 numbers there, and we'll ascribe the first 5 numbers A1. So those first 5 numbers will represent the passing down of the A1 allele. And the next set of 5 numbers will ascribe A2. So that will represent the passing down of the A2 allele. So in order to see what our next generation, our 5 tiger offspring alleles look like, if there was random mating among the parents, we will randomly select now 10 numbers to represent those 10 alleles that we expect to see from, of course, this distribution of numbers above. So let's do that. All right, so we've randomly selected our numbers, and here are our new set. So we selected first number 0. And because that falls between 0 and 4, that would then represent the passing down of A1. We then selected number 1, and again 1 is between 0 and 4, so in that case we'll call an A1 allele being passed down. We then selected 5, and because that's between 5 and 9 here, we would then consider the A2 allele to be passed down. And so we've of course done this 10 times. And we have this nice collection of alleles that will be passed down to the next generation. And then we can say, okay, the first two numbers here represent offspring number 1 in this new generation. The second set of numbers would represent offspring number 2. The third set offspring number 3, and so forth, number 4 and number 5. So number 1 here would have the genotype A1A1. Number 2 would have the genotype A2A1. We've then got number 3 being homozygous, 4 being homozygous, and 5 being heterozygous. So we can take this information, and just as we've done before, we can calculate the allele frequencies. So the allele frequency here for A1 is 0.6, and the allele frequency for A2 is 0.4. So what do you notice about those numbers? Well, they're actually different than the parents. So recall that the parents now had allele frequencies in their population of P equaling Q. So we had A1 being 0.5 and A2 being 0.5 in terms of their allele frequencies. Now we've got 0.6 and 0.4. So there's been a change in this population, a change from the parents to the offspring only by this sort of random process. There are no other factors influencing this population. We simply have simulated a random process, and there is a change. So this would indicate perhaps an evolutionary change, and this is really the realm of genetic drift. So let's do this process now, this random process, which we've just done for one generation, for one population of 5 tigers, producing 5 offspring. Let's do this now for a slightly larger population. Let's do it for a population of 10 individuals, and we'll actually do it not only for one population, but we'll do it for 5 populations. And we'll carry that simulation out across not only one generation, but multiple generations. So we'll start here at 0, and we'll carry it out all the way until we reach 20 generations. And we'll chart the fate of our A1 allele. And remember, this is just a random process. There's no other factors influencing the frequency of A1 here, just randomness. So we start now with all of our populations having an allele frequency of A1 as 0.5. So 50% of the individuals in that population carry the A1 allele. And then, of course, each one of the lines you see in this graph represent a different population, but each one is starting essentially the same. And again, those populations are 10 individuals. So a pretty small population here, small population of, let's say, tigers. And what do you notice? Well, first of all, if you look at the overall graph, you see that there's a lot of scatter here. These populations are behaving very differently. A1 here, the frequency of A1 is kind of all over the board. I think more importantly, if you look at some populations, like population number 1 and population number 3, you see that in fact they go extinct. They are expunged, they are removed, they are lost from the population. So in the case of this population, after 11 generations, that allele is gone. And after 13 generations, that allele is gone from population 3. So we've had nothing but randomness causing the loss of those alleles. You also notice here at the top of this graph that some populations, like population 5 and like population 2, have A1 becoming fixed in the population. In other words, They are the only allele at that particular gene in the population, indicating that the other allele, A2, is gone. So we only have one population here out of our 5 that actually retain both alleles. Okay, so let's now do this one more time. We'll simulate the exact same process, but we'll do it not only with a population of 10, we'll now switch to populations of 200. Same graph, same information, 5 populations, all beginning with an allele frequency for A1 of 0.5. And what do you notice immediately? Well, right away you can see there's not a lot of difference between these populations. They're all pretty similar in the way that they're behaving over time. We don't have some populations shooting up and becoming fixed. We don't have cases in which A1 is lost from the population. Same process. The only difference here is that we've got many more individuals. So larger populations are more buffered against the effects that randomness, that drift here, can cause. Smaller populations are much more susceptible to change because of this random process, because there are fewer individuals. So drift here affects smaller populations much more than larger populations. The effect of drift is much more magnified in those small populations. I think that's the key takeaway point here. So when populations are very small, drift can lead to the loss of particular alleles. It can lead to some alleles becoming fixed in a population again. And this can lead perhaps to lower genetic diversity within the population. It can also lead to pretty strong changes in allele frequencies between perhaps isolated populations, which may make them quite different in a short amount of time. So I'm going to pass you over to my colleague Terry, who will build a spreadsheet and run you through a nice spreadsheet exercise that will demonstrate genetic drift and much of what we've covered.